Okay, so welcome to um, the online meeting for maths, MTH129, Discrete Maths. So this week I was going to look at um, recurrence relations. So recurrence relations are used for lots of sort of things. So I guess the application that we have in mind for this particular subject for computer science students is primarily counting number of operations for a recursive function. That's where it sort of comes from. Um, but I would like, but it's useful in many other situations. So this sort of idea of um, having a starting value and then producing other ones from it is common in various fields. And so Kalman filters, you'd see it in for predicting location. Um, so for Hawkeye, for example, which is in cricket, how Hawkeye works, which is trying to work out where the ball is. It uses cameras to work at the current position of the ball, then uses a slightly more complicated recurrence formula to work out what the next position of the ball is based on its spin and gravity, etc. So it works at the new location, and then it checks that location compared to what the camera sees and adjusts it. And so it's using quite a big feedback operation, but essentially it's more complicated recurrence relation, really. One you can't solve directly, but that sort of idea is used all sorts of fields. That's sort of a reason why we want to do it. But they're useful in just their own right, as just in terms of population, etc. So there's a few skills that I want people to have when they're doing recurrence relations. And that is, so first thing is, I want you to understand how to utilize them, which really just means subbing them in. And so let's just do one as practice. So basically, a recurrence relation is just a way of generating a sequence of numbers. So this first sequence is going to be A0, which is 1, that's told to you. And then A1 equals something, A2 equals something. And so in order to work out any value, we basically just need to sub it in. So we've got an initial condition, which is how we start. It's my kids in the background you can hear, unfortunately. Well, normally they make nice noises, but they're being not too nice today. That's okay. So say initial condition, and we've got a recurrence relation. So this is how it's been done. And I would normally think of it as being is you've got a value is equal to the previous value plus 1. And so A1 is the new value we want is equal to the previous value, which is 1 plus 1. So you give you 1 plus 1 or 2. And A2 here, again, would be equal to the previous value, which is 2 plus 1. It's equal to 3. And then A3 would be the previous value plus 1, which is 4. So that's the idea of subbing in. So really just you understand this formula is just a way of working out the next value based on the previous few values. That's all it is. And so how I've written it in lectures and how I've written here is slightly different. But instead of trying to understand it basically in terms of indices, it's just going current value, previous values. I think that's the clearest way of understanding it. This case here, what the goal is to find a general formula for the nth case. So what's the formula for, so the nth would be like, what would be the value for the thousands number in the sequence, etc. So you can type in what would be the general formula. So an is equal to what? And most of the time, the formula would be something to do with n's, essentially. So any idea what the formula might be? And again, we're just guessing the pattern for the moment. So we're not trying to prove it in a formal sense. Just more observation to start with. Okay, yep. N plus 1. That's great. And so the first sort of skill I want, as I'm trying to demonstrate, is just the idea of being able to sub into a recurrent relation just to generate values. And the sense of what we want to do with these recurrent relations is we tend to want to solve them, just like we did there. So we wanted to actually get a solution, and a solution really is getting a general answer, that sort of idea. So I want to do the same thing for a few more. Let's just try C for the moment. So I've got some initial conditions. So I've got D naught is 1, D1 is 1. So I've got some starting points. So the next thing I want to do is work at D2. And this recurrent relation here basically says to work at any value, there's a relationship. So you've got a value, so D2 here is the value we have in mind. Then we have minus 3 times the value before it. So the difference between these ones, that would be Dn plus 1 is the value before it. So the value before that would be D1 plus 2 times the value before that, which is D0. Now you can think of it, I'm just subbing n equals 0 into this equation. That's perfectly fine. Or you can just understand this thing as saying one value depends on the previous one. So subbing everything I know. So I've got D2 minus 3 times by 1 plus 2 times by 1 equals 0. So if you plug them in, D2 minus 3 plus 2. So D2 minus 1 equals 0, or we simply have D2 is equal to 1. And you can do the same sort of thing if you plug in to work out what D3 is. You do the same idea. So you've got the same equation, D3 minus 3 times the one before that plus 2 times the one before that is equal to 0. And if you plug the numbers in, so that's 1, that's 1, then again you get that equal to 1. And what do you reckon the pattern is in this case? So what's the general solution, I guess is what I'm looking for? Yeah, that's right. So that the general solution we have for this is that d to the n is just equal to 1. And so again, just the idea of subbing in, the goal is to find the general sort of solution. So far these two examples have been give you straightforward answers, but not everything always is a pattern you can necessarily see. So let's just try E here. So I said the bottom one. So again, we've got D naught equals 1, D1 equals 3. So you can see slightly different initial condition. So same recurrent relationship, so exactly the same sort of relationship between them, but you're starting with slightly different values. And again, this is trying to show that slightly different values do give, at first glance, quite different looking answers. So for a recurrent relationship, you need to know the actual relation itself and the initial conditions. Both are really important to give you a sense of what the answer is going to be. So to work out the next one, so D, so D2 minus 3, D1 plus 2D0 equals 0. So what's D2? So if you plug the numbers in, maybe you can type things in. So D2 minus 3 times 3 is 9, plus 2 times 1 is 2. And so D2 is equal to 7 in this case. And you do the same sort of thing for D3. So D3 minus 3 times the one before it, plus 2 times by the one before that, is equal to 0. D2 is 7, 3 sevens are 21. D1 is 3, 2 threes are 6. And you plug that all in and you're getting D3 equals 15. So if I'm doing too fast, let me know. So can you see the pattern? Maybe you can. So the goal for this is to work out what D to the n is equal to. Now there's a pattern here you might be able to see, or you might not be able to. So if you're listening, or Dylan, you're here. So if you want to, you can just write on your own piece of paper what you reckon the guess is if you want to. Let's assume you can't see what the pattern is. Although you might spot it, often they get harder to see just from looking at a bunch of numbers. And so we want to have some sort of method which we'll give the answer to. So the method I've taught in lectures, there's two different ones I've considered. One is the Gerarding function method, which otherwise I won't mention. I won't show you today, and the other one's the characteristic equation method. I think that most students will find the characteristic equation method preferable, and as I've mentioned in announcements, for example, I will always give you the choice in assessment item, so you can choose which one you want to pick. Where sometimes it's a bit magic where the answers come from, the characteristic equation method. You can actually show it's not magic by doing the Gerarding function. It actually produces everything quite explicitly, if you want to see it that way. But I think if you just take on a faith value that these things work, characteristic equation is pretty good. Okay, so characteristic equation method. Step one is to get the characteristic equation. That's what it really comes down to. So we get the equation, which ends up being a polynomial. Then we solve it. Then we get our general solution. And what I mean by a general solution is something which solves just the relation part. So just that part. And then lastly, we want to use the initial conditions to get the particular solution. So we want to use the initial conditions part to get the actual solution we want for the whole set, rather than just the general recurrence relation. We want to do it for the other bits too, because that makes a difference. So that's the basic idea. So characteristic equation part, that's what you need to do. So we need to get the characteristic equation. So formally speaking, you just replace dn, or whatever sequence might be, by r to the power of n. That's basically the idea. And then go from there. In practice, though, the approach, what it is the recurrence relationship is basically each of these terms is based on some previous ones. So how you do it in practice is you find the bottom term. So the bottom term is ddn in this case. And so you just write that as a 1. So I look down I've got d to the n plus 2 minus 3 times by something plus 2 times by something equals 0. That's the basic formula of recurrence relation. So you get the characteristic equation really just involves changing these dn things into powers of r. That's what that really boils down to. What it essentially simplifies down to is the bottom term ends up being 1. The next term above that corresponds to an r. The term above that would be r squared. If you ever come to it, the term above that would be r cubed, the term above that would be r to the 4. So you always think of as terms as being 1, the one above it, the one above that. And so the characteristic equation really is just converting the bottom term to 1 and each subsequent term to that being multiplied by r. And that's how you work them out in practice. And as you can see, you can just write it down. So the characteristic equation is r squared minus 3r plus 2 equals 0 in this situation. So how I mentioned in lectures is to actually literally sub it into this, literally sub that into the equation and then cancel, then divide by the smallest power of r to get this sort of equation, but you can go straight there. What else was I saying? So essentially what this is doing, in case you're trying to think, well, what's the purpose of it all, is really just guessing a solution. So what happens is, under the right circumstances, then the solutions for d to the n look like that. That's what the solutions actually look like. And so we're trying it out and going, if that's what the solution look like, we would like to work out what the r is to match that pattern. So really are guessing a solution type. That's where it boils down to. And so it's useful to know that's where it comes from as the whole process. Now you've got the characteristic equation, now you need to solve it. So you need to work out what the r values which solve this equation, which sort of special cases of r to the n actually will solve for you. So can you tell me what the solutions to that equation are? Okay, so r equals 2 and a 1, and again, so the way to do that in general is to factorize if you can, and if you can't factorize, use quadratic formula for this sort of case. And it's important to know that, so for people who need it, the characteristic, the quadratic formula, so if you've got a r squared, I've done this slope slide. So you've got AR squared plus AR plus C equals 0. And the solutions, if you can't factorize quickly, would be minus B plus or minus the square root of B squared minus 4AC, all divided by 2A. And the plus case and the minus case give you the two different solutions. And it's important, I think, for everybody to know that formula. And what I mean by knowing this subject means have it in a piece of paper that you can copy down quickly and utilize in practice. That's really important to remember, which is why I just want to put it down to emphasize it. Okay, so we've got our solutions. Right, anything. So we've got characteristic equation, it's 1. Got our solution. Now from that, we can then just write down a general solution. So the general solution is pretty much any number, let's call it K1 for the moment, times by the first solution to the power n, plus another number times by the second solution to the power n. And so again, the characteristic says that we've got basic solutions of the form r to the n, and we know that r is either 2 or 1. That's what the 2 to the n and 1 to the n correspond to. And then in general, it's just what's called a linear combination of those, which is that sort of format. And so anytime you've got that sort of equation, the solution will always have that sort of format. And depends upon the initial conditions, what the values of K1 and K2 actually are. And again, we could, I will make this a little bit simpler. I can say K1, whatever that might be, times 2 to the n plus K2. The reason being, 1 to any power is always going to be 1. So let's just save a little bit of writing. So that's the general solution. And again, it's just a matter of writing it down. And there's just a key pattern to it. There's a slight little caveat, which I'll mention later in the next example. So once you've got that, just use initial conditions, what these K values are. And so we know that D0's 1. So if you plug n equals 0 into this sort of format, we're getting K1, 2 to the 0, plus K2. Or putting it another way, 2 to the 0 is just 1. So we can write it in as K1 plus K2. Okay. The other thing, that's one initial condition, that's the first of them. The other one we have is that D1 is 3. So again, plugging n equals 1 into this, we're getting K1 times by 2 to the 1, or just 2, plus K2. And now it's a matter of solving these simultaneously. So Dylan, do you can tell me what the answers are? So what's K1? What's K2? So again, if you're watching a recording, have a go, see if you can work it out yourself. What I would do, simultaneous equations, to try eliminating a variable, for example. So you can either make K2 the subject of this first equation and sub it into the second one. That's one approach. Or you can take the differences of these equations to eliminate a variable. They're the sort of two basic approaches. So what I would do in this case would be the second equation here minus the first. We'll get rid of the K2s. And you can see that K1 ends up being 2 in that case. And K2 ends up being minus 1 for it all to work out. And so by eliminating the variables and getting rid of the K2s, I can solve K1, and to work at K2, I can just plug in 2 into, say, the first equation, make K2 the subject, and get the answer. Now, I skipped working there, naturally. If you want any more, just ask for it. You go, explain how I got that. That's okay. But if you're happy we'll leave it at that. But I'm trying to do the bigger picture here. So now you know what those sort of values are. We can now find the actual solution. This is the particular solution we're actually looking for. And that dn is equal to K1, which is 2 times by 2 to the n, plus our next value minus 1 times by 1 to the n, or just 1 really. And so that's equal to, that's correct, but you can write that as 2 to the n plus 1 minus 1 if you wanted to. And so you might have noticed that if you looked at the answers above, 1, 3, 7, 15 are all the different powers of 2 minus 1. And depending how well you know your powers of 2, you might have recognised that in the first instance. Or maybe not. So the purpose for doing this is, even if you can't see the pattern, this characteristic equation method gives you a nice, good way of generating the answers. So the next one I do is another characteristic, another recurrence relation. And again, you could plug a few numbers in to get the next few values. But I want to solve it by the characteristic equation method. So we do the same approach as before. We get our characteristic equation. And so look at this thing here. The bottom term is e to the n. So we replace that by just a 1. The next term above that is e to the n plus 1. We replace that by r. And the term above that would be e to the n plus 2. And we replace that by r squared. So we can sort of write down our characteristic equation. And again, if you wanted to, you could write more steps, but that's the basic approach. The next thing would be to solve it. So, what is the solutions to that? So what is r equal to? If you try to solve that quadratic equation, what answer do you get? Any ideas? We've still got, oh yeah, good. I was about to say, do I still have you? Not worried my internet connection had died too much. Okay. So if you factorize this, you're getting r minus 3 squared equals 0. That's really good to see that. And so if you solve it equal to 0, it's tempting to write maybe just down 3. But I think a better approach, which is what you've done there, which is fantastic, is to realize there really is 2 solutions. They just happen to be the same. So for a quadratic equation, I always just like to say that there is, in the right definition, there is always 2 solutions. Sometimes they happen to be the same, and it's in that case we'll call it a double root. And realizing it's a double root is really important with the next step, as I'll explain. So well done there. So the next step, as I said before, is to get this general solution. So the general solution is to say e to the n is equal to some constant times the first root to the power of n plus another constant times the second root to the power of n. That's like what we said before. It does not quite right. It's not going to quite work out though. If you look at what I've written down here, is both these terms here are actually the same, effectively, just some number times 3 at the end. And so they'll just sort of collapse together. And so when you've got a double root, just writing these 2 things down isn't going to be enough to cut it. So we actually need a second basic solution. So this is our first basic solution, and this is another one. And so we need to do some sort of approach to get our second basic solution. Now, if you use the generating function method, you'll see that the second solution that you require has an n out the front of it. So the second solution is an n to the n. It's probably going to be easier just to learn that's what the second formula takes, rather than have to use that generating function method to actually produce it explicitly. And so for double roots, this is the key thing. So for a double root, we're going to have this n term cropping up. That's the main difference between these 2 examples we've seen so far. So for this first example, the roots were distinct. So distinct roots there. And so we had the 2 terms by themselves. This one here is we've got a double root, and so we have to put an n term in front of the other one. That's the main thing to learn. Once you've done that, the same approach is the same really, and that is you sub in initial conditions like we did before. So if you're subbing n equals 0, you're getting k1 times by 3 to the 0 plus k2 times, well, n0, just make it 0. 3 to 0 is 1, just k1. So we can see quickly k1 is 0, which is pretty good. The other initial condition we've got is 1 is equal to e to the 1. That's equal to k1, something which we've already realized doesn't count anymore. So it's equal to K2 times by 1 times by 3 to the 1. And so we can see that 3 K2 is equal to 1, or K2 is a third. So putting it all together, reading e to the n is 1/3 n3 to the n, or putting it in a slightly different format, n3 n minus 1. So that's our general solution. So this characteristic equation method, you can see, produces these things nicely. So the characteristic equation method really works well because these sorts of equations have very predictable basic solution types. And then you combine these basic solution types to form the general solution. Initial conditions give you a particular one. And so the sorts of recurrence relationships they work really well on are linear. Linear just means every e term is sort of by itself, perhaps with a constant in the front of it, and just summing or subtracting them. So no multiplication, no powers. That's what linear means. It's got to have constant coefficients. So all the numbers in front of all the e's are constant numbers. And the other thing is homogeneous. So homogeneous means you've got an equal 0 over on the other side here. So the characteristic equation can be adapted for inhomogeneous cases. I'm not going to do that explicitly in the subject. So there's a few instances where we might do them in ad hoc sort of thing, but certainly I won't assess that because I just haven't done enough examples. But so the characteristic equation method really works in that special case, but nevertheless, though it might be a special case, it comes often enough, and it really is using the fact that we know the basic solution types. And a generating function method is more powerful because it can actually show that explicitly they're their solution types and can handle more broader things as well. So that's the trade-off. But again, I suspect most people just want to better work the answer out, and this method works really nicely. Okay, so just want to do one more example. So it's a lot of words here, but just write it out. Just write it out. So basically, these sort of stuff is good for modeling populations. So I've just done a simple one. So I've got a bunch of mice, and they're sort of two groups of mice. They can either be adults or babies. Just a really simple description of them, I guess. You could make it more complicated by having babies, juveniles, adults, old age. You can have quite a few tiers if you wanted to. The approach is similar. So I've got a bunch of adult mice. MN is the adult mice, and a bunch of baby mice is the Bs. What happens is that they don't all live, unfortunately. Fortunately, depends what you think of mice. So we suppose that the survival rate is 50%. So putting it as an equation, the number of adults in 1 month is equal to half the population of the adults from the previous month. So half of them have died. So we've got only half. So half of them have survived. Putting it away. Then the babies have grown up, but only half the babies have not survived. Half have. And so this first equation here says half the adults have survived and stayed adults. Half the babies have survived and grown up to be adults. That's the first survival rate. Although there's lots of them dying, lots get born too. And so the birth rate is 6 babies per adult per month. So the number of babies born is equal to 6 times the number of adults. So babies can't breed, but adults can. And so these first two equations really are just capturing the so the 0.5 from the MN is just the survival rate of adults. The 0.5 in BN is the survival rate of babies to adults, which in I mean, I think in real mass populations, they will probably be different numbers, by the way. But let's make it easier. And the 6 corresponds to the birth rate. And so this sort of concept is just modeling population. So although I've picked numbers to give a nice answer at the end, you could utilize this to model populations much more sophisticatedly. And instead of, as I said, you could have lots of different levels. And so this, you still need initial conditions to get it working. So let's assume that initially we start with no adults at all and 14 units, which is 14,000 baby mice to begin with. So we start with lots and want to see what happens. So at first glance, you go, well, this seems a bit different to what we've done before. It's got not one variable, but 2 variables sort of intertwined. And although that seems more complicated, it so happens that you can rearrange these sorts of equations very easily into just one variable. So you can collapse it down just to a simple recurrence relation. And so I'll explain how to do it. The thing I want to focus on more is the solving this recurrence relationship. But essentially, broadly speaking, we can just sub some things in. So we want to know some initial conditions. So when we've got 2 variables, we need to have know what M0 is, which is fine. We just know what M1 is, and to work that out, you just go plug in an equation. So we know what M1 he would be given by this sort of formula, which is a half. So the number of adult mice in 1 after month is half what it was from the 0th month. So after 0 is nothing, plus a half times the number of babies in the previous month. So half a lot of 14. So half 0 plus half 14 gives you just a total of 7. So subbing in gives you an initial condition. We also want to try to get the number of adult mice in terms of just adult mice. Don't have any babies in there. So you get this second equation. The number of babies in any month is 6 times by the number of adults in the previous month. So when we got number of adult mice is the number of mice in the previous one plus a half times babies. It's just going to be the number of adult mice in the month before whatever this index is, which corresponds to Mn minus 2. And you can see this quickly go from one to the other, which is nice. And you can go backwards too in some sense. So I have explained it, but there is a way of going from this equation just by itself and splitting up into a so this is a second order linear homogeneous. This is a second order linear recurrence relationship. There is mechanisms to be able to split them up into 2 coupled ones, which are both first order. So there's techniques to go backwards and forwards. They're both useful, but we're going to focus more on these ones. So once we have this sort of relationship, we want to be able to solve it, and try to answer sort of questions about it for the situation we have in mind. So approach is the same sort of way. So we want to get the characteristic equation. So the characteristic equation would be find the lowest term, call that 1. So it'd be 3 times by 1. The next term would be R, so 0.5 R, got an equal sign, and the highest term would be R squared. Same trick I did before. We don't have to solve it. So standard thing to sort of solve it is to tuck everything in the one side. Like that. I shouldn't make mistakes. I should make that a minus sign to be correct. At this point in time, it's got fractions in it, and so either use quadratic form straight away. It might be quicker for you. I'm going to try to factorize. So to do that, I find it easier to see things if I get rid of fractions. So I'm going to multiply everything by 2. So I've got 2r squared minus r minus 6 is 0. And once that, I can give a good stab at trying to factorize it. And so the 2R here, I'm going to split as a 2R and an R. This -6, I can split a few ways. I can do as 1 and a 6, alternating signs, or 3 and a 2. So it's going to do trial and error. So I'll try 3 and a 2. So I got 2 2s before and 3. That seems pretty good. So I got 2 times 2R times 2 gives you -4, plus 3 times R gives you -1, which is good. That's exactly what we want to do. So what I'm doing here, just trying to explain myself a bit more, I've just split up the first term and the second term as some sort of products. So the top one's the easy one to do. And then once I've done that, I just trial and error one sort of pattern which matches up. And then once I've tried when I want to check my answer, I'll just expand it out to make sure that middle term is actually accurate. By splitting out the factors, I'll make the end term will definitely work. It's just the middle one if that's the issue. And that gives me a factor. And so I can see, yep. So what's the answer? So therefore, once you do that, what's the solution? What's the values of R that correspond to that? Yep, sounds good. So the solutions, which is step 2, is R is equal to 2 or -1.5. And the plus, because it's plus, you have to do the minus solution. Then you write the general solution. So the number of adult mice is some constant. Don't know yet. K1, the first solution is power of n, plus K2, the second solution, the power of n. And it's important to put brackets here. So the fact it's a -1.5, when you do the powers, it's going to alternate between positive and negative all the time. And then last, we need to plug in some initial conditions. So 0 is M0. And plug in 0 to this, both powers would be just to the power of 0, which just ends up being 1. So, as is very commonly the case, when you're tucking in 0, you just get a pretty simple looking form. When you sub in 1, you're getting 2 K1 and then -1.5 K2. So you need to get practice. As you get more practice, you realize, oh, I can write it more simply. Instead of seeing it as just a big lump of symbols on the page, you can go, oh, okay, I'm always going to do this sort of pattern, and you can understand the bigger picture as you're doing it, and you're not going to get lost in the detail. So the hardest part of algebra is it just seems lots of detail. Certainly this sort of, I imagine looking at this, for some people, there's just so many details even on what the page are written down here. You need to try to see the bigger picture, which is what I'm trying to focus on today. And like anything, practice is what you need to do. Anyway, so what we've got those two, now we're going to try to solve them. And again, I'm going to try to do elimination. So I'm going to do equation 2, it's got a 2k. I'm going to subtract off 2 lots of equation 1 just to get rid of the k1s. And I picked that one because it just seems an easy thing to multiply by. So 7 minus 2 lots of 0 gives you 7. 2k1 minus 2 lots of k1 gives you 0. It's the right construction. Sorry, I'm just being interrupted. I'm having a lecture at the moment, right, Ellie? Can you please come back to me in a few minutes? Okay, just have a. Okay, that sounds good. Sorry about that. Fatherly duties. See you soon, Ellie. Okay. Where was I? So minus 1.5 K2 minus 2 lots of K2 would give you minus 1.5 minus another 2 gives you minus 3.5 K2. If you divide both sides by minus 3.5, you get minus 2, which is a nice number. So I manufactured this situation. And then you can plug that back in anything you want to. So I would plug it back into here, for example. So K1 minus 2 equals 0. And so K1 equals 2. And so our general solution is the number of adult mice, in terms of thousands, would be K1, so 2 times 2 to the n, minus 2 times by minus 1.5 to the power of n. And so, knowing that that's the answer, so this is a number of thousands of adult mice over time, you can start answering some sort of questions. And I always got to give a sense for it all. You can will with various things. So we want to go, well, what's the number of baby mice, for example? We've got a number of adults, how many babies are there? And if you look back at the original equation, the number of baby mice is equal to 6 times the number of adult mice in the previous month. And so you can just plug various things in. So it's going to be 6. In the previous month, it'd be 1 less power. So instead of 2 to the n plus 1, we'll just have 2 to the n. And minus 1.5, the previous month would be minus 1.5 to the power of n minus 1. And I just have to remove the 6 here. So minus 2 times 6 will be minus 12. So that sort of is the basic approach. And you want to know that for n equals 0, etc. And you can simplify it down, but that looks fine to me. So you can work a number of babies and adults at any point in time. And you might go, well, something that's worthwhile noting, there's some special behavior here, is let's do the number of babies divided by the number of adults. So what's the ratio, essentially, of babies to adults in the population? And how it worked out, if back look at the original question. So we actually had no adults to begin with. So you start with none. So the ratio was all babies, all babies, no adults. Then after 1 month, basically all the babies would grow up to be adults and then have no babies. So the ratio flips the other way around. So there's a bit of toing and fro to begin with. But as time goes on, things start to settle down. So it's a transient period. But after a while, for these sorts of problems, the ratio tends to settle down. So for linear problems, I should say. So if you've got a linear problem, you get these sort of nice ratios. Non-linear, bit of a different story. So it's good to look at how this ratio does. So b to the n is 6 times 2 to the n minus 12 minus 1.5 to the n minus 1. All over 2 to the n plus 1 minus 2 minus 1.5 to the n. So, and again, that number is going to change, but it settles after a while. So I want to use some of these ideas that we've learned from Big O of trying to estimate sort of things, what happens as n gets big. So as n gets big, what happens? So Big O is a type of asymptotic notation, which is a very fancy way of saying what happens as things get bigger. What happens as n grows? So as the number of months goes on, what happens to it? So we learnt with Big O, there's an order to things. So you can see the function's really here. on the top, apart from ignoring the constants at the moment, which is what big O does, are really just all exponentials. And so big O tells us an order to things. So they're all exponentials, so they're all the same basic class. But when you have few exponentials next to each other, the exponentials which dominate are the ones which are the higher base. So therefore, on top, this first term will dominate because it's 2 rather than 1.5. So 2 is bigger than minus 1.5. So that will dominate. And I'm ignoring the plus and minus signs. And again, similarly, the 2 to the n plus 1 will dominate over here. Now, unlike big O, I do need to worry about the constant at the front. That will make a difference. But nevertheless, this first term with the 6 on it will, after a while, be much bigger than the other term here, and that really won't be that significant. So the same ideas we learn in big O we can apply here, and knowing that order is important for many things, not just doing algorithms. So now you've got this sort of ratio we can cancel out, and so the 2 to the n and the 2 to the n disappear, and so we're left with 6 on 2 or 3. So the ratio of baby mice to adult mice is 3, so it's a ratio of 3 to 1. So baby mice to adult mice is, after a while, in the ratio of 3 to 1. And it gets, and as n gets bigger, it gets closer to that. So I'll put it another way. That was right. So about 75% of the population of these mice are babies and 25% are adults. So heavily juvenile sort of population. And again, it's a made-up situation, right? So I've made them up to make nice figures, but you could adapt it to make it much more realistic. And so these sort of, there is some nice properties with these sort of linear cases, and understanding how things grow really is actually an important technique in many aspects, not just computing but population here. So that just gives you an idea of some things I expect you to do. So you should now be able to finish the last assignment, which is due in about a week's time from when I'm doing this lecture. And the things I expect you to do, I expect you to sub in to recurrence relationships, just to demonstrate you understand what they're about, really. So just to understand them. I would like you to solve them generally, which is what we've been doing, using either the characteristic equation or the generating function method, either or. And I expect you better do it for both distinct roots and double roots, because in both methods they come across a bit differently. So it's either the main things I want you to be able to do. I was trying to encourage you to think through some more things this last example. And I do expect you to better answer the problem when it's wordier like this one. So I've got a bit more of a wordier example. So question 2, I think is quite accessible. I do have some more things in this drill which I won't get to work out through here. And that is, you can use generating function methods to do stuff. So they're starred because they're harder, but generating function methods can start to do harder situations. So this one here, is still different to the previous cases because it has a plus 3 to the n here. So this is called a non-homogeneous equation because it has a term which doesn't have any f's in it, any of these sort of sequence terms. And so the generating function method can handle these things just quite naturally. And so just again, stressing, that's why I mentioned all approaches. That's distinctly harder, and I don't see the point of asking those sort of questions in an assessment item but it depends on your maths ability. You might be keen to give it a go. You can do other things. I said this question 4 is similar to that taking ratio I just did a second ago. But anyway, thanks for your time. If you've got any questions you'd like to ask me about assignment 3 or 4 in particular, so assignment 4 is looking at algorithms. So certainly I've put an algorithm, the merge sort algorithm, which is a bit harder to work out how many costs it is. That's a recursive idea. But just trying to get you to think through how you might use some of these things. But I've made it very guided. So although it's much harder to solve, I've tried not to force you to do much of the solution yourself, but just to see how it works. But there are questions like what we've been doing today there. Okay, let's see if I can find you. Let's look at the question. I might be able to answer your question.